Alrighty then. So, since I'm not there to answer a lot of questions, let's just do answering questions like this. I'll just go through basically how I would solve these problems, and if you're having trouble with a problem, come find it. I'll do them in sets of 5. Why not? Okay, so this one's looking at problem 1 through 5 on assignment 1, waves 1. Okay, so that first one is telling us that a sound wave has a frequency of 256 hertz, and we're looking for what the wavelength of that wave is. Okay, so we're looking for our wavelength, and we've got our frequency of 256 hertz. Okay, now we're looking for wave speed. Okay, so the, no, we're looking for wavelength. Haha. The wave speed is actually a known quantity for this one. And this is actually one that I've gotten a couple of emails on, just because people were confused as to what speed we're going to use, right? We've got a whole bunch of different speeds for the speed of sound. We've got it going through air and water and steel. We've got one for different temperatures in air. Okay, if it doesn't tell you any of that information, like if it doesn't tell you that it's in water, or it doesn't tell you it's in steel, we're going to assume that it's in its normal state that we're going to be observing sound in, that being in air. Okay. Also, if it doesn't tell you temperature, you assume that it's at room temperature, and we're just going with our very first value that we had for the speed of sound, that being 343. Okay. So if we're looking for that wavelength there, we've got this speed equals wavelength times frequency formula, our wave speed formula. So if we're looking for lambda, we're just going to move that around. So we would just do lambda equals your V over your F. All right. I'm not going to plug it in for you. You can do that yourself. All right. So that's number 1. All right. Number 2. Okay. We're still looking at a sound wave, which means that we automatically know that our speed is 343 unless told otherwise. And we've got a wavelength of 0.664 meters. Okay. So our lambda is 0.664 meters, and our frequency is what we're trying to find on this one. So we're just going to move that formula around a little bit differently. Instead of looking for lambda, now we're just looking for frequency. So we're just going to take our speed and divide it by our wavelength. Okay, and again, not going to solve that one for you. Do it yourself. Okay, so now we've got a sound wave with a frequency of 125 hertz and a wavelength of 2.8 meters. And it's asking us to figure out what the speed is. So since it's actually giving us numbers, that means we can calculate what our wave speed is, and we're not just going to use that 343. Okay, so for this one, it gave us a wavelength and a frequency, and we're looking for what V is. We don't need to move our formula around here. We're just going to plug stuff in, our wavelength and our frequency. So our frequency is 125. Our wavelength is, what was it? 2.8. There we go. Okay, so then we just plug those numbers in and get our speed in meters per second. Okay, next one, number 4. What is the speed of sound in air when the air temperature is 2 degrees Celsius? So this one actually does require us to use that one new formula that we got. Okay, so it's telling us that our temperature is 2 degrees Celsius, and that is the unit that you want it in. If you were to have a formula or a question that gave it to you in Fahrenheit or Kelvin or any other measurement of temperature, you would need to convert that, or you would need to find a different formula for finding that speed correction at different temperatures, because that one is specifically just for in Celsius. Okay. So it's just telling us that temperature there, and we're looking for the speed, which means that we're going to use that formula that we got, where the speed of sound in air is just going to be 331 plus 0.6 times t. Okay, so if you didn't watch the third part of the notes on that, the second part had a typo there. All right, I said 0.6, but I wrote down 0.06. So make sure when you're calculating those speeds of sound at different temperatures, you've got the right formula there. Okay, so for number 4, you're just plugging in 2 degrees Celsius for T there and finding V. For number 5, you're just going to be plugging in, what was it, 26 degrees? Yeah, 26 degrees Celsius. Okay, and then you just plug that into the same formula. Get 2 different speeds entirely based on the temperature there. Okay, so that's 1 through 5 on assignment 1. Next video is going to cover 6 through 10. Okay, so now looking at 6 through 10 on waves 1. All right, number 6 is saying that we've got a sound wave with a frequency of 256 hertz. So we know our F is 256 hertz. Okay, this is number 6. And let's see what else is given us. The air temperature is 26 degrees Celsius, so we've got T, and as soon as you see temperature involved, that means that we're looking at the speed of sound at different temperatures formula. All right, you don't want to use 343 when you've got a temperature, unless that temperature happens to be room temperature. Okay, so 20 degrees would be room temperature. So it's telling us we're at 26 degrees, and we're looking for the wavelength of the wave. Now on number 5, we actually did find out what speed corresponds to 26 degrees. Okay, but let's say that we didn't, so that we go through the entire process here. All right, so we're ultimately looking for what the wavelength of this wave is. Okay, so to find that wavelength, the formula that we've got that has wavelength and frequency in it is this one. The speed of the wave equals that wavelength times frequency. Solving for wavelength, that would just be the speed of the wave divided by your frequency. Now we've got our frequency, but I'm assuming that we don't have our speed of the wave. All right, you would have calculated it already on number 5, but you know, let's talk about how we're finding it, just in case you skipped it for some reason. All right, so we've got our temperature here, which means that we can calculate what the speed of that wave would be. All right, because when we're looking at speed of sound in air, that's just going to be 331 plus 0.6 times our temperature. Okay, so to figure out what the speed of sound at that temperature would be, we're just going to plug 26 in there for T. All right, solve for whatever the speed of our wave would be, plug that in there, divide by our frequency. That'll give us our wavelength. Okay, so we're using both of these formulas together. So just look at what your known data is, and you'll be able to work your way through. All right, next one, number 7. We've got a sound wave with a frequency of 340 and a wavelength of 0.985. And we're looking for the air temperature, right? So we're still using these same two formulas, except we're going to use the wavelength and the frequency to figure out what our speed is. Okay, so looking at our known data, we've got our frequency of 340 hertz. Okay, we've got our wavelength of 0.985 meters. All right, and we're trying to find the temperature of the air. Okay, so these two together, the frequency and the wavelength, that can give us the speed of the wave. Okay, all right, usually I write that in the opposite order, but you know, multiplication, you can move it around. So once we've got our speed, then we can just use that formula again to figure out what our temperature is, just moving that thing around. So moving our 331 over, so that'd be V minus 331, and then dividing by 0.6 to get that off the temperature. Okay, so we can figure out our temperature using that. All right, number 8, 9, and 10 are all asking about things that were on that little visual thing that was on the notes, the wavelength of red and violet, and then there was a little video that was attached that talked about pink. But let's talk about that now. Okay, so red light, that is the highest wavelength that we can see, the longest wavelength. Okay, and that one ends up at around, it is a range of numbers. Red's kind of hard to pin down. You know, colors are just how we're perceiving things, and we don't have perfect vision where we can see things on a hertz by hertz scale or a nanometer by nanometer scale. All right, so it's a range of stuff that we consider to be red. All right, and red is round about 700 nanometers. Okay, so looking at those prefixes, nano's one that we've seen before. Nano means times 10 to the negative 9th. Okay, so this would be 700 times 10 to the negative 9th. Okay, or if you wanted to express it in scientific notation, then that would just be 7 times 10 to the negative 7th meters. Okay, so your wavelength of violet light, that's going to be the shortest wavelength that we can see. All right, so that's going to be 400 nanometers-ish, around there. Okay, again, that one is a range of values. All right, so that one would be 400 times 10 to the negative 9th meters, or 4 times 10 to the negative 7th meters, if you wanted to put it into scientific notation. All right, number 10 is a trick, okay? Because if you're looking at a color wheel, right, if you were doing one of those in art class, it makes a nice little circle, all right, where you've got all those colors around in a circle, and they kind of blend into one another. But when you're looking at the visual spectrum, it's not a circle. It's a straight line, where you've got high values on one end, low values on the other end. If you try and loop it back together to make a circle, yeah, it makes a nice pretty diagram, but that's not what is physically happening. All right, your eye can tell the difference between red and violet. Okay, so when it sees something that is a combination of those two, it just mixes them together. All right. So when we're looking at pink, it doesn't have a specific frequency, but it's because it's a combination of two different colors. All right. Like green light has a specific wavelength. Blue light has a specific wavelength. Yellow light has a specific wavelength. Pink is always going to be a combination of two different wavelengths of light because it's made from two different sides of that visual spectrum. Okay. There's no such thing as pure pink light. It does not exist. Pink does not have a wavelength. Pink has no wavelength. And that's not to say that pink doesn't exist. It just isn't a color by itself. All right, continuing on, going through 11 through 15. All right, so 11, we're looking at light now. Okay, so it tells us a beam of light is traveling through water and has a frequency of 4.5 times 10 to the 14th hertz. So we have our frequency, 4.5 times 10 to the 14th hertz. Okay, I apologize if these powers of 10 are difficult with like a phone calculator, just in case you don't have a scientific one. I just thought of that being an issue. Okay, so if you're on a computer, I'm sure that you can look up a scientific calculator to be able to handle that. Or if you can't find one of those, you can plug in any sort of equation with scientific notation and stuff like that into Wolfram Alpha, in case you haven't found that wonderful site before. All right, so just go to Wolfram Alpha, and it'll be able to, that's an A, Wolfram Alpha, and it'll be able to handle those powers of 10. Stop focusing like that. Good. Distracts me. Okay, so it gave us the frequency there, and we've got a wavelength of 5.02 times 10 to the negative 7th. Okay, so we've got 5.02 times 10 to the negative 7th for our meters there, and we're looking for the speed of light wave in water. Now, usually we would know the speed of light, but it is in a different medium, so it is going to be going a little bit slower. Basically, those little light particles and the wave itself is going to be bouncing off of the stuff that's in the water, and total, the photons are still going to be going the same speed, but because they're bouncing between different things, they'll be covering less distance in the same amount of time because they're traveling a greater distance from one point to another. They just keep bouncing around on the way there. Okay, so we do not know what V is. It's not just going to be C on this one because we're not in a vacuum or in air. We're in water. Okay, so you can just use speed of a wave formula, V equals F times lambda. And we're done. All right, number 12, we're looking for the wavelength of a radio wave whose frequency is 4.5 times 10 to the 4th waves. All right, 10 to the 4th hertz. Yeah. So main thing about this one, radio waves, whenever they show up in problems, they like to cause problems with people just because they aren't sure what type of wave it is. Like you listen to a radio. So a lot of people use the speed of a sound wave when we're looking at radio waves, but radio waves are just another frequency of light. They're on the electromagnetic frequency spectrum. Okay, so when we're looking at those, it behaves just like color would. It's just outside of what we can see with our eyes. Okay, so when we're looking at a radio wave, that's still just light. All right, and it isn't telling us anything about the medium there, which means that we're going to assume that V just equals C, that 3 times 10 to the 8th. 3 times 10 to the 8th meters per second. Okay, so it's telling us that we've got a radio wave, and our frequency is 4.5 times 10 to the 4th. Okay, so 4.5 times 10 to the 4th hertz. Okay, and we're just looking for what lambda is. So that would just be lambda equals the speed of your wave divided by the frequency of that wave. And again, that speed there is going to be the speed of light because radio is a light wave, just one that we can't see. Okay. 13, lightning strikes off in the distance and you hear the thunder. 10.0 seconds later, approximately how far away did the lightning strike? Okay. So we're still looking at well, all right, so we've got two different types of waves that are moving here. You've got the lightning, so you're seeing something going towards you, but the question is asking how long until you hear it. or you hear it 10 seconds later and you figure out how far away it is based on that. Okay, so if you were able to time how long it took for you to see it, that could also calculate how far away it is, but you would be looking at a light wave for that. Since we're focusing on how long it takes for us to hear it, we're going to be looking at a sound wave. Okay, so for this one, it's giving us a time, we've got a speed, and we're looking for a distance. So we're going back to our very old friend, Formula 0. Okay, so the speed here, because it isn't telling us anything about temperature or medium, we're just going to be using the normal speed of sound in air, the 343 meters per second. The time it gave us, that's not period, that's not frequency, that's the time it took for that sound wave to travel to us. Okay, so we're using that lowercase t, that was 10 seconds. All right, and we're looking for x. We don't know what that is, all right, but we can just use v equals x over t. Okay, number 14. Okay, for this one, Sasha yells at Boris, and Boris hears her 0.211 seconds later. How far is Sasha from Boris? Okay, so this is actually the exact same problem as the other one, right? We've got a time, we've got a speed, and we're looking for distance, okay? The only difference is the time that we're using. Okay, so we still got 343 for our speed of sound. Our time is a lot shorter because they're closer together. So that'd be 0.211 seconds, and we're looking for x. Might as well solve that thing for x, multiplying our t to the other side. X is just going to be v times t. Okay. All right, last one for this video. 15. Boris. No, Bjorn. Yodels at a canyon wall and hears his echo 2.5 seconds later. How far is Bjorn from the canyon wall? All right, now this one, echoes, you need to be careful with echoes and reflections. All right, because if we're thinking about Bjorn shouting at a wall, okay, here's Bjorn, all right, here's our canyon wall. Okay, if we're thinking about this wave traveling, it told us that it took 2.5 seconds for him to hear his echo. Okay, so if we're thinking about that wave, it is traveling from him to the wall, and then it has to come back from the wall to him. Okay, so total, that 2.5 was the time it took to go twice the distance that we're trying to find, because we're just looking for the distance between him and the wall, not the total distance that the wave traveled. Okay, so be careful with this one. All right, there's two ways you can handle it. You can either just divide the time that it gave you by 2. All right, so instead of using 2.5 seconds, just use 1.25 seconds, because that's how long it would take to go from him to the wall, just that one distance. Or you could use the 2.5 seconds, find the distance there, and then that is the total distance traveled by the wave, so just divide it by 2. And that would give you the distance traveled by the wave just one direction instead of there and then back. Okay, so on number 15, and anytime that you're looking at an echo, make sure you're paying attention to how much total distance is being traveled. All right, so that was number 15. We just got a few more to go. Let's go. All right, number 16, very similar to number 15. All right, so it's telling us that we've got an echo that is 2.5 seconds later. So again, remember that we are looking at an echo. That 2.5 seconds was how long it took to go from my dog, schematic diagram of my dog, from my dog to the wall and then back. Okay, so when we're looking at that time, usually I would just do the time it gave for the total and just divide it by 2. Okay, so instead of 2.5, I'm just going to use 1.25 seconds. Okay, the speed of that wave is going to be different than in the last problem simply because it's giving us a temperature. Okay, so usually we would use that 343 for the speed of sound in air, but because we don't, well, we actually know more information, we know what temperature it's at, we are going to have to use the 331 plus 0.6 times T. Okay, so that T was told to us the temperature there. That is just the, where was it? It was 4 degrees Celsius. Okay, so once we've got that speed there, just using that formula, then we're just going to use the same one that we used last time, the x equals v times t. Okay, so, yeah, hold on, did I write that one right last time? I did. Okay, just making sure I'm not a total idiot. All right, so for that one and for anything with an echo, make sure you're paying attention to the total distance there and the total time. All right, number 17, same sort of deal. We've got astronauts putting reflectors on the moon. We've got a time there. Okay, so it's telling us how long it took for that wave to go from the Earth to the moon and then back. Now, the time it gave us was 2.666 seconds. Okay, so because we're looking at an echo, that means it would take half the time to get from us to the moon. Okay, so the time that we're going to be using, if we're looking for the distance to the moon, is going to be half of that. We're going to use, instead of 2.66, we're going to use 1.333. Okay, so that's the time it took. We're looking at a laser being fired, so we're going to be using the speed of light. All right, so that V there, we're just going to be using 3 times 10 to the 8th meters per second. Okay, and then we're looking for that x there, so we're still going to be doing x equals v times t. All right, number 18, we've got the sun being a distance from the Earth, and we're looking for how many minutes it takes for light to travel from the sun to the Earth. Okay, so we've got a distance there. Main thing to pay attention to on this one is it gave us our answer in kilometers. Okay, so it told us that our distance was 1.55 times 10 to the 8th kilometers. Okay, so kilo means times 10 to the 3rd. So since we got that kilo there, if we want to get it into meters, we're just going to add 3 to our exponent. All right, so that would just be 1.55 times 10 to the 11th meters. Okay, so in meters, that's how far away we are. And then we're looking at light again. So we're looking for how many minutes it takes. Okay, so we've got our speed for this. We got our 3 times 10 to the 8th because we're looking at light. Okay, and we're looking for that time there. So starting off with formula 0, v equals x over t. Okay, solving for our time. We're just going to put that x over on top of our speed. All right, so that distance, the 1.55 times 10 to the 11th meters, divided by our velocity of 3 times 10 to the 8th, that will give us our time. Just be careful because this time that it's giving to us is in seconds. Okay, so whatever you get for this, divide it by 60 because it wanted how many minutes. All right, so it should be about 8.5 minutes, somewhere around there. Okay, so then number 19, continuing along the same line of questioning as number 18. All right, so the spacecraft is halfway between the Earth and the Sun when it explodes, which means that our distance is just going to be half of whatever that is. Okay, we're looking for how many seconds pass before people on the Earth see the flash from the explosion. Okay, so for this one, if you're looking for the time there, you can just look at the time that you found for number 18 in seconds, and then just divide it by 2 to find the time it would take for light halfway along that path to make it to the Earth. The light isn't accelerating. If we're cutting the distance in half, we'll be cutting the time in half as well. Okay, so A, just take whatever time you had in seconds for number 18 and divide it by 2. For B, that one is a trick. Okay, because even assuming that sound waves were able to travel in space, you still would never hear that thing. If you've got something half the distance from the Earth to the sun, right, those sound waves, they're propagating out spherically. Even if they were able to travel in a vacuum, they would spread out so much that you wouldn't be able to hear it regardless once it got to the Earth. But the main thing there is that a sound wave needs particles to move around. If it doesn't have any particles, it's not going to travel. Okay, so for B, they're never going to hear it. For 2 reasons. One, if it was actually traveling through a vacuum, which it's not, it would have spread out to the point that you wouldn't be able to hear it. And 2, sound waves don't travel in a vacuum. Neat. And we're done with assignment number 1. Hurrah! Okay, so I'm going to be uploading these intermittently. Cool. Good luck, guys.